Does redirecting program I/O to a file or to another program change your program's behavior? Most people would say no. Let's take a look. Welcome back, everybody. Today I want to look at an issue that one of my students was having a few weeks back. It was an issue that was just making them a little crazy, and the first time I saw it, this also threw me a little bit, so I thought it'd be a good one to look at together. So let's dig into it and see what we can learn from this. But before we do, a big thanks to all of you who support this channel, both on Patreon, buying merch, liking videos, subscribing to the channel. I really appreciate it. For those of you that are new, I do post weekly videos every Tuesday. Subscribe to the channel if you don't want to miss them. But so now, without further ado, let's take a look at the code. Because today's story starts with a simple scenario like this. You probably recognize this, hopefully. It's Hello World, and if I come in here and I run it, so I can compile it, I guess I already did, and if I run it, then it works. So right, nothing interesting here. It's just basically the simplest program you can imagine, and it's working, seems to be working just fine. But if I run it again, but now redirect the output to a file, something like this, now it's segfaults. So this is the situation that my student presented me with. Of course, there was one other relevant detail, and that is that we were working with a custom memory allocator that the student had written. But what baffled the student was that the bug didn't surface when the program was run normally. Right? When we just run it normally, it doesn't surface, doesn't show up. Redirecting the output to a file, that just changes where the output ends up, right? It shouldn't change the behavior of the program, right? This should work exactly the same, right? So the student starts thinking maybe this is a problem in the terminal, maybe this is an operating system bug, maybe who knows. But nope, it was actually a problem with their memory allocator. And there's nothing really too odd about that, right? I mean, segfaults, super common, pretty much they're everywhere in student code, especially when we're building custom memory allocators. But the fact that it only shows up when we redirect output, that threw them off. Because we all tend to believe that redirection doesn't change anything, but it actually does, or at least it can change stuff. Now, before we dive too deep into this, I want to emphasize one thing, and that is that what I'm about to show you may work differently on different operating systems. So I'm running Linux here. You can see here, if you're interested in my information about the version I'm running, this is what happens on my machine. But I'm not 100% sure, even with different versions of Linux, that this is going to behave the same on your machine, on your operating system, on whatever else, however you've got your system set up. But that said, I still think this example is really illustrative, even if it doesn't show up on your machine. So let's take a look. So first of all, anytime we have a segfault, the first thing that should come to mind is let's look in our debugger. So let's run this program in GDB. Let's give ourselves a little more space here. And then we want to run it. Now, just like before, if we run it in here, you can see Hello World, it works just like we would expect, just like we saw in the terminal. And of course, we know that this bug only surfaces when we redirect. So what I'm going to do here is we'll just redirect the output. I don't know if you knew you could do this, but when in GDB, you can run a program with redirected output from GDB. So we're going to do that. And if we do that, then you can see we hit our segfault. And in this case, it crashes in malloc. Like I said, there's a problem with the memory allocator. This is actually a problem that I injected specifically, but let's take a quick look at it. Let's jump over to our allocator. So if you look at the allocator, now I did make a video recently about replacing your memory allocator, why that might be an interesting and good idea. This allocator is basically a slightly modified version of the one that I did in that video. So check it out if you missed that video. Basically, the only changes I made is I removed the part where we filled the allocated blocks with debug-friendly bytes, and I added a fake bug right up here that basically just segfaults anytime you call malloc with a block that's bigger than 1024. And I did this just to keep things simple for demonstration purposes. The point is that this allocator will work just fine on small blocks. Anything smaller than 1K, it's just going to pass them through to the system allocator, which we got a pointer to using DLSim. But anytime I try to allocate something bigger than 1K, it's going to break. And of course, my student's bug wasn't this intentional. Obviously, they weren't trying to crash, but they were handling large and small blocks differently, and their allocator was crashing when the blocks got large. And again, that's not all that crazy, but it leaves us with two questions here. One is, who's calling malloc? I mean, in this program where basically this is Hello World, who's calling malloc here? And two, why does it only show up when we redirect output? Okay, so if we get back in GDB, we're taking a look at here, and let's set a breakpoint in allocator.c on line 14. I'm doing this specifying the file name and the line number so that it doesn't get confused. I want to make sure it gets the right version of malloc. Maybe it would anyway, I don't know. But now if I run this, basically you can see it stops in malloc just fine. So we do have an allocation. So somebody is calling malloc. Let's just take a quick look up here. We'll look at our backtrace and you can see, well, there's a bunch of different calls that are made, but they all originate from printf, right? So printf is allocating memory. Well, it doesn't actually directly allocate memory, but it calls functions that eventually allocate memory. And this memory is being used for buffering your output to make things faster. So that's interesting. That's cool. You notice that it's allocating a block of size 1024. That's great. But now let's look at what happens when we run it and we redirect our output to a file. Yes, we want to restart it. Okay, so now we stop in the same place. Things look almost exactly the same, except you notice that the size of the block that we're allocating is now 8K, not 1K. And why is that? Well, when we ran it with the redirected output, we actually changed the buffering mode for the program. And now libc is saying, this output's gonna go to a file or a pipe or something else, so it doesn't need to be quite as interactive. So let's buffer more of the data before we push it. That'll make things a little faster. But in this case, now that the buffer size is larger, our allocator crashes where it didn't before. And now the mystery makes sense. And I just wanted to show you that, one, in case you ever get to writing your own custom allocators, this bug might come up for you. But two, just to give you some insight into how things work under the hood and how things like redirection, which we usually think of as not changing our program behavior, actually can change how things work and cause a program that normally was working to all of a sudden stop working. It's also great to get some debugging practice. I hope you learned something from it. Like the video if you did, subscribe so you don't miss next week's video. And until next week, happy coding, my friends.